Today's video will be a look at the mirror and thin lens equations. It's the same equations regardless of using mirrors or thin lenses. We've only seen mirrors, curved mirrors so far, so we're going to ignore the thin lens part of it. That'll come in later, but that'll be handy because when we do that later, you won't need a long video for that. Version of these notes can be found on Monday, June 8th, and there's a few links there as well. Textbook reference on pages 467 and 469 can be found here. It's a pretty good textbook. It'll break down a handful of equations and show you a few extra things. So don't be afraid to click on that link. As far as the assignment's concerned, I'm only going to assign questions 1 to 6. You can try 7 to 15 if you want, but they're for lenses. The equations are the same. It's just they'd be drawn differently if you go to draw them afterwards. So moving on. Quick little reminder. When you have a curved mirror, you place an object in front of it, it should produce an image. Depending where you put this object, the image might be inverted, it might be erect, it might be real, it might be virtual. There's 7 different cases for that. 6 for the concave mirrors, 1 case for the convex mirrors. So these would be converging mirrors where all the light rays tend to converge upon one spot, and this will diverge the light rays and spread them all out. A few little terms, just as a quick reminder. The focal point is the point where all the parallel light rays should converge upon on a converging mirror, and that is the focal length when you measure the physical distance from the vertex to the actual focal point. So we're going to be working with the focal length today. The center of curvature is typically seen as the radius of curvature if we actually measure that distance from the vertex to C. So it behaves as the center of whatever your curved mirror is. The object distance is found from measuring basically the length between the object and the vertex, because we make all our measurements from the vertex. The image distance will also be the measurement from where the image is to the vertex. And I forgot to mention, the focal length is going to be half the distance of the radius, or if you know where the length of the center curvature is, just divide that in 2, and you can get your principal focus, otherwise known as your focal length. Your diverging mirrors, they basically all the same definitions. We measure everything from the vertex, but the only main difference when you have a diverging mirror, so a convex surface, your focal length is going to be negative because it's actually on the virtual side of the mirror. Your image distance will also be negative because it's on the opposite side of the mirror. So anytime you have a virtual image, the image distance will be negative. Anytime you have an inverted image, the height will be negative. I don't have it on this little screen here, but HO would be the height of the object. So that would just be measured from the principal axis up to the top of the object. And HI is the height of the image, which is measured again from the principal axis, in this case down to the bottom of the image, or in the case of the convex mirror, up to the top of the image. So we always measure our heights from the principal axis. I'll get into magnification in a second. So these are the technically 4 equations that you're going to be working with. I'm not going to break down where this really comes from, or either of these really come from, mainly because it's a lot of geometry and I want to try to keep this video nice and short. A quick little YouTube search, or even just an online search, and you'll find some textbooks that'll walk you through where these come from. In my experience, most grade 11 students just want the equation and they want to go. So the equation to relate the object distance, image distance, and the focal length is seen as a reciprocal addition. So do not, under any circumstances, associate the 1 over DO plus 1 over DI is equal to 1 over F as the same as just saying DO plus DI is equal to F. It doesn't work that way, right? 2 plus 3 is equal to 5. 1 over 2 plus 1 over 3 is not equal to 1 over 5. Right? That's not how fractions work. So don't do that kind of math ever. Over here is technically 3 equations, right? It's a magnification ratio. So your magnification is just your image height divided by your object height. If your image is bigger, for instance, right, if we measure our object to be 1 centimeter tall and our image reflected from the mirror ends up being 2 centimeters tall, we'd have a magnification of 2, right? It's twice as big. Likewise, if this was 0.5, your image height was 0.5 centimeters and your object height was still at 1 centimeters, then your magnification is half, right? It's 0.5 for a magnification. Magnification can mean larger or smaller, it doesn't matter. The same magnification can be calculated by the ratio of the image distance divided by your object distance, but it's the negative ratio. So that negative symbol is a beast because it is often forgotten when students do math. So do keep in mind that negative is attached to these D's. Whether or not you want it to be negative DI or whether or not you want the negative to be attached to the DO, it doesn't really matter where that negative is, top or bottom. So in essence, you have 3 different equations. Did I say 4 earlier? I meant 3. You have your magnification is equal to the ratio of your height of the image divided by the height of the object. You have your magnification equal to the negative image distance divided by your object distance. And you could just get rid of the M altogether and just pretend you don't see it and relate these 2 guys together, because very often that's what you're going to do, try to find either the image distance or the height of the image or any of the other 2. So there is some signage towards it as well. So for instance, if your image height of the image is positive, that means that the image is erect, it's standing upright. If it's negative, it's inverted. The magnification, if it's positive, we see it as erect. So this is assuming also that your height of the object is measuring upwards. We just typically assume that whatever the orientation is of your object, it's just going to be positive, typically. So therefore, if your magnification is positive, then your image is erect. If your magnification is negative, then it's inverted. So that's based on this guy right here, right? So if you suddenly stick a negative in there, it's going to be upside down. As far as focal length is concerned, you can tell what kind of mirror you have. If it's positive, you have a measured focal length that's positive, that means you have a converging mirror. So in other words, it's a concave surface. If you have a negative focal length, that means it's diverging. In other words, a convex mirror surface. And then of course, image distance, if you have a positive DI, so if this guy ends up being positive, regardless of the fact there's a negative there, if your image distance is positive, it's a real image, it can form on a screen. If it's negative, it's virtual and it cannot be formed on the screen. So these signages, positive negatives, will tell us image characteristics when you guys do your math, because you're always going to have to write down your image characteristics after you solve a problem. So let's get to it. I end up taking too long explaining these problems, so you do it 1 or 2 different ways. Suppose you have an object is located 30 centimeters from a converging mirror with a radius of curvature of 10 centimeters. At what distance from the mirror will the image be formed? And then part B will do after. So typically write down what you know. Object distance is 30 centimeters. It's 3 sig figs. Radius is 10 centimeters. And of course, that's your radius of curvature. So that means your center of curvature is at 10 centimeters. And therefore, your focal point is at half that distance. Your focal point would be at 5 centimeters. Therefore, your focal length is 5 centimeters from the vertex. And if I were to diagram that out, right, it would kind of look like this. I just kind of grabbed some rulers from the old internets, and I put in the object height, which was given to me. So therefore, I kind of drew this on the computer to make sure the object height was 4 centimeters up from the vertex. I measured up from 30, because that's where I put the ruler. I measured out 10 centimeter. If I go down with the mouse, 10 centimeters for the center of curvature, and my principal focus is 5 centimeters. So 25 and 20 measured from 30. So I'm going to try to draw this to scale as good as possible on the computer screen. And I have a slide. This is a parabolic curvature, obviously, because I want this thing to be perfect. So let's get at her. The 3 rules say any light ray parallel to the principal axis should reflect the principal focus. So I drew that one in. I don't expect you guys to draw these for every single problem. I'm just going to kind of relate to you that, hey, the math works out. So this is just sort of we're going to get the answers, math using the diagrams first, and then I'll walk you through the math. The second rule said any light ray traveling through the principal focus just reflects through the parallel to the principal axis. And if you zoom in, it looks like it's around 8 millimeters from the principal axis. So in other words, 0.8 centimeters. So, and the third rule says any light ray traveling through the center of curvature is just going to reflect back down its original path. So that third rule is nice and easy. It's just one line. You just put arrows going towards the mirror and away from the mirror, and all of them intersect at this point right here. And if you kind of use the mouse, it looks like it's about, so I moved this thing earlier when I took this out. It looks like it's about from 31, 2, 3, 4, 5, 6 centimeters from the actual mirror. So oh, there you go. I forgot I did that in this animation. So it's 6 centimeters from the vertex. So I know where my image should form. I actually got my answer right there without doing the math. So you can double check your work. I know what my image distance is. I know what my height is going to be. It's upside down, it's down below the principal axis. So I've got a height of 8 centimeters, and the negative just means it's below, but otherwise my height is 0.8 centimeters. So, and I know from this diagram, I can figure out my image characteristics. I know it's smaller because my, if I look at the absolute values, my object, which was 4 centimeters tall, is bigger than my image height, which is 0.8 centimeters. So regardless of the fact that it's negative, I don't care if it's negative. I'm just looking at the magnitude. 4 centimeters is bigger than 0.8 centimeters. I know it's inverted. Not only can I see that, but I can tell from just the measurement, the fact that I have to go down, HO is positive and HI is negative, and therefore, since they're different, it's upside down. I know the location should be between the center of curvature and the principal focus, because if the center of curvature is at 10 centimeters and my principal focus is at 5 centimeters, and I drew, I'll also calculate this in a minute, but I drew that my DI, my image distance, was found at 6 centimeters. That's between the two, so I know it's between C and F. And because I'm measured on the same side of my vertex, so I'm on the same side as my object, therefore my image distance is considered positive. So therefore it's a real image. And that's just case number 3, if you remember from a previous video. So I could have just looked up, oh, this looks like case number 3. I know what these should be. But these are my numerical values that I'm now associating with it. Because before we weren't worried about the numbers. Okay, so I've got my answers using qualitative methods, drawn them out, but here's how we'll do it mathematically. So I'll just get rid of that for now. We know what the answers are going to be. I'll just prove it mathematically. If we take my relationship of my object distance and my image distance, add the reciprocals of those to my principal, should be equal to the reciprocal of the principal focus, I'm looking for the image distance. So that means I'm going to have to move my my reciprocal of the object distance to the right-hand side of the equation. So when I do that, I have to just subtract both sides by 1 over DO. So that will cancel out nicely. And then on the right-hand side, I just have 1 over the focal length minus 1 over the object distance. And that's not good enough because I have 2 fractions, and you can't just subtract 2 fractions. So that means you have to find a common denominator. So when you find the common denominator, you basically multiply both fractions by each other's denominators. Since I'm not going to work with the numbers, I'm just going to work with the symbols. So in order to have the common denominator, I need both principal focus and object distance in my denominator. So multiply this top and bottom by DO, multiply this top and bottom by F, and you should end up with that when you have a common denominator. It doesn't matter what order you write that in, DO or F can be first, doesn't really matter. And so I have now 1 fraction on the left, reciprocal of my image distance, and I have 1 fraction on my right. It's very important that you have a single fraction on the left and a single fraction on the right before you do this next step. Next step is to take the reciprocal of them. So that means you just flip both sides of the equation. You can't do that at the beginning because you have 2 fractions on one side and 1 fraction on the other. You can't do that at this stage either because you still have 2 fractions on one side. You can only do this reciprocal if you have 1 fraction on each side of the equation. So you basically just flip the numerator and the denominator around, and since when you flip 1 over DI, you just have DI over 1, which therefore you could ignore the over 1. But on my right-hand side, I've got my focal length multiplied by my object distance, all divided by my object distance minus the focal length. And so that's the equation we're going to use. I prefer students use this equation mainly because you don't make mistakes with repeating decimals. And you'll see that in the next way I show how to do this. So stealing that equation, and if you had to solve for the object distance, you basically do the exact same thing, but obviously you bring 1 over di over instead. And if you had to solve for the focal length, you would just leave the two together and just find the common denominator for 1 over do and 1 over di, and there wouldn't be a subtraction, it'd all be addition. All right, moving forward, plugging in the numbers. All right, you guys are experts at this point in your lives. So focal length is 5 centimeters, object distance is 30 centimeters. Multiply them together, find the difference between those two lengths. So 30 minus 5, and you end up with 150 centimeters squared, because a centimeter times a centimeter is a centimeter square. The square gets canceled off by the centimeter down below, and 150 divided by 25 is going to be 6. All right, easy peasy. So 2 significant figures times 3 significant figures should just give you 2 significant figures in the end. Okay, as far as the subtraction is concerned, we have the same precision, so that's why we still keep that extra decimal there. And since if you are going to draw this out yourself anyhow, that's about the precision you can actually measure, which is to the nearest millimeter. And the fact that I got 6 centimeters is great. It's a positive 6 centimeters because if you remember, that's what I drew earlier, right? I drew this to be from there to there. They all collide at that exact point at 6 centimeters. I haven't quite done the height yet. That's next. But first, I'm just going to show you different ways. Some students prefer doing it this other way. They claim it's less room, or less work. But in my experience, I find it's also the method where most mistakes happen. But I'll show it to you anyways. So skipping a couple of steps, this is the second way you could have done this. Let's just assume the first few steps are the same. You want di by itself, right? So we'll rehash all of this. I'll just go as far as solving for di. So once you get to this stage of the game, 1 over di is equal to the reciprocal of the focal length minus the reciprocal of the object distance. Some students will just start plugging their numbers in there, and that's fine. Because there's typically one of two buttons on your calculator. There's either a button that's x to the negative 1 on your calculator, or else it just says this on your calculator. There's one of those two buttons. I don't know which one you have in your calculator. And essentially, they would just type in 5, press that button, and it'll flip it automatically to 0.2. It won't show you the units, so the centimeters stay down below. Essentially, this is 1 divided by 5. That should give you 0.2. And then in your calculator, you just hit subtract, and you type 30, and then press again one of these two buttons, and then it'll automatically give you 0.03 repeating. I didn't go forever, but I just typed it enough times to prove a point. It's a repeating decimal. Too often, a student will look at this, because some students, I don't know who you are when you do your work, some students hit erase after every single time. 1 over 5, 0.2, great, write it down, erase. 30, press one of these buttons. You get 0.3 repeating. Some students interpret that as 0.03, and that's all they would write down. That is not the same as 0.03 repeating. So I need to make myself very clear, because I know there is a method which will avoid any rounding issues. If you follow this method, I expect you to keep that whole number in your calculator, because repeating decimals shouldn't be, so fractions are perfect ratios, repeating decimals shouldn't be altered when I know that there is a better method to do it, so there shouldn't be any mistakes. But most of you have calculators where you can just pretty much do this all in one big long step anyways. If you want to write it down on your own piece of paper, you can just say 0.03 with the bar over top of just 3, because it's just 3 that's repeating. I hope that's how you were taught how to do that in middle school. So then you would just do that math, and you'd find that you should get, if you subtract those two, you get 0.16 repeating. Yeah, so that's what you should have in your calculator. And so what that basically means is you have the reciprocal of your image distance is equal to 0.16 repeating over a centimeter, because again, only the number got divided out. So the centimeter is still in the denominator. And so we just have one final step to make. Don't make the common mistake that some students will say, oh, the image distance is 0.16 repeating. No, the reciprocal of the image distance is 0.16 repeating. So you'd have to still take the reciprocal of that, and then you just press that button again, 1 over x or x to the negative 1, and it will find the reciprocal for you, and it will give you exactly the same value of 6 centimeters. Right? If you would have called this 0.03 and not considered the repeating factor, it might say your answer is 5.8 or 5.9. I can't quite remember, but it won't be exactly the same. And when I know there's an exact answer, I'm going to want that exact answer. Just as a heads up, I don't really care which way you do it. Just make sure you know how to work your calculator when it comes to repeating decimals. So either way, both methods gave us an image distance of 6 centimeters, not 0.6, 6 centimeters is an image distance. So now we can go to part B. If the object is 4 centimeters tall, how tall is the image? So I'm just going to go straight to this equation. The ratio of my image height to my object height should be equal to the negative ratio of my image distance divided by my object distance. I'll make it smaller so I have room. If I multiply out, I don't want that HO in the denominator, so I'll multiply by HO on both sides to get rid of it. On the left-hand side, I'm left with just HI. On the right-hand side, I've got the negative of image distance multiplied by the object distance, all divided by the object distance, object height. Plug in the numbers, you know the numbers, you solve for, so this is where errors happen. If you didn't get 6.0 centimeters exactly, then you probably have something slightly different here, which means your height is slightly different. But you should exactly have 6 because method 1 says you get 6 perfectly. Just multiply stuff through. One of the centimeters on the top gets canceled out, and you should end up with a negative, because again, don't forget that negative, 0.8 centimeters or 8 millimeters. You would have 2 significant figures, because again, 2 sig figs here, 2 sig figs there. There's 3 on the bottom, but you should just have 2 in the end. If you were drawing this out, you wouldn't actually be able to measure that extra digit. Most you don't have rulers that would do that. And so that is what earlier I found when I drew it all to scale. I'm not going to draw, I don't expect you to draw them all to scale. I'm just telling you that's a way you can double check your work. It just takes a little while to do it. So I got negative 0.8 centimeters, that's great. So now I can actually see for myself that, okay, and this is, again, the SALT, the image characteristics, you can just recognize, oh, this is case number 3, and therefore I just know what my image characteristics would be. But mathematically, this is how you determine, without the diagram and maybe without recognizing which case it is, I know that my image should be smaller because, again, my height is 0.8 centimeters, where my image, where my height of the object was 4 centimeters. I could also figure that out using the ratio of my distances, right? My object distance was much further away from the mirror than my image distance, which would imply that it's smaller. Likewise with the inversion, I calculated a negative height in the end, so therefore I should have an inverted image. I know it's between C and F because I know the numerical values of my center of curvature is 10, and therefore my focal point is at 5 centimeters. And if I calculate image distance to 6, that should be between them. And I know it's real because my image distance is positive. If the image distance was negative, I would have a virtual image. So you can always compare this to your cases and try to visualize what the condition actually is. So I did one, I went really long through it. I've got one more after this, but if you get the idea and you just want to get to work, by all means, stop the video. I'll do a diverging example right now. So hopefully this doesn't take too long. I'm not going to draw this one out to scale though. So suppose you have a diverging mirror with a focal length of 5 centimeters and it produces an image that is located 3.75 centimeters from the mirror. How far away is the object from the mirror? What is the magnification? So I just grabbed a screen capture from the last time I drew one of these on the screen for you, video ago. I basically have this, so this one's not to scale to our problem, but this is essentially what we have. I said when it comes to convex mirrors, so that's your diverging mirror, so unfortunately has 2 names. There is only one case. No matter where I put this object from that curved mirror, my image is going to form somewhere between my principal focus and my vertex. My image is going to form somewhere over here. If I move this object closer to the mirror, my image is going to form closer to the vertex. As I move my object further away, my image is going to get closer to my principal focus. It'll never go past my principal focus. It'll always be somewhere between F and V. So really there are just one single set of image characteristics. As soon as you hear, oh, I've got a convex mirror or a diverging mirror, I know these are my image characteristics. There is only one possibility. I have to get a virtual image. So that brings me to numbers. I was told it was a diverging mirror, therefore my principal focus has to be negative. It's not negative up here where it says 5 centimeters because it said you had a diverging mirror, or I could have told you that you had a convex mirror. So it's just up to you to know that it's negative. I know that a convex mirror will only produce virtual images. So if it says an image is located 3.75 centimeters from the mirror. Because of the type of mirror, I know it has to be a negative 3.75 centimeters. So this is kind of a jerk question. It assumes that you remember certain things like, oh, whether or not it produces a virtual image. So this one's tricky, and that's why I'm adding it in the video. So the question is, how far away is the object from the mirror? So it wants to know where this object is placed. And the second part of the question is, what is the magnification? So I don't know anything about the heights, so that's irrelevant. I'm just looking for magnification afterwards. Okay, so using the relationship between the object distance, image distance, and the focal length, using the same methodology as the previous question, you would solve for DO. So hopefully you wrote it down. If not, just rewind the video a little bit and get to this state where your object distance is equal to your focal length times your image distance, all divided by the image distance minus the focal length. So that's where I'm going to solve for it because I prefer this method. After that, you plug in all your numbers, right? Your focal length is a negative value, your image distance is a negative value, a negative times a negative should yield you a positive. So 5 times 3.75 centimeters gives you 18.75 centimeters squared. It should just be 3 sig figs, but I'm not done, so I'm going to keep all my digits. My denominator is my image distance, so negative 3.75 centimeters minus the negative, because the focal length is negative. So I've got a negative minus a negative, so that becomes plus 5 centimeters. So negative 3.5 centimeters plus 5 centimeters gives you 1.25 centimeters. And then at that point, this square will cancel off by the centimeter down below. And if you do that quick division, you'll find that your object distance is 15 centimeters from the mirror. So that is nice and far away compared to your image distance, right? And this isn't to scale, but it's kind of a rough idea. Yeah, this is a lot closer and this is a lot further. And that's typically what you'll see. Unless you really bring the object really close to the vertex, then it's hard to tell which one. The object will technically be further, but it's still often look the same distance. Those are strange circumstances. Okay, so that's my object distance. From there, I would calculate my magnification. So I'm going to use the ratio of my image height divided by my object height because I don't know, sorry, distance, not height. I got ahead of myself in my head. I don't know what my heights are, so the other magnification equation is HI over HO, but I don't know what my heights are, so I'm going to use the image distance divided by the object distance, but please, please, please remember about the negative. And so from there, again, just plug in your numbers, right? Negative 3.75, so the negative and the negative. Too often, if this number is negative, people forget about the other negative number. So do be careful. So if you do that quick division, those two negatives become a positive, and you'll end up with 3 sig figs divided by 3 sig figs should give you 3 sig figs. And you end up with 0.25, which means your magnification is 1/4. So the image is going to be 1/4 the size of the object. So because of that, I can figure out my image characteristics. I know that my image is smaller because my magnification is less than 1. So typically if your magnification is 1, then you're the same size, right? But if that's the case, then I know my object's at my center of curvature and I don't have a converging mirror. So my object would be the same size if that was equal to 1, but since my magnification is less than 1, it's smaller. If it's greater than 1, it's larger. My attitude is erect because in the end, I have a positive magnification. My location is between F and V because, well, it's a convex mirror, and so you just either need to remember that or just even look at what's given to you. My focal length is 5 centimeters. My image is 3.5 centimeters, right? Whether or not they're both positive or both negative, this should be enough to tell you that, hey, this is closer to the mirror than the principal focus. And so therefore, it's between F and V, okay? As far as type, diverging mirrors, convex mirrors will only produce virtual images. So typically, I just figure out whether it's virtual or real by saying, hey, is DI positive or negative? Well, it's hard to tell from the question because it gave it to you as a positive number. So you just have to know that diverging mirrors, otherwise known as convex mirrors, are only going to produce virtual images, right? Because if you kept that as positive 3.75 in the question, you wouldn't have calculated the correct object distance. Yeah, you'll just have to kind of remember that fact. There's nothing more I can tell you you about that. But if you were to calculate, say, your focal length, and you ended up with a negative value in the ends, that's usually a good indication that you have a diverging mirror. Anyways, I hope that was helpful. I'm going to stop because I reminded myself in the video to stop. Email me if you have any questions.